Okay, I just posted the recording from yesterday. I got it a little late last night, but it's up there. The other announcement about the web page is that one of you pointed out, if you were not enrolled in Online Dynamics 1 last semester, you still, despite my best efforts, you didn't have access to it. There's a link now, which you could in principle click on, which I made sure there is one yet. But again, if you're not enrolled, apparently you cannot reach that page. If you still want to have the homeworks, exams, access to the recordings, and the only way I can see that happen now is that you would have to email me, and then I personally enroll you retroactively in that course, which is easy to do. I just add your name. And then you will also have access to the recordings from last semester and all the written materials. You already do have access to the lecture notes, which I emailed everyone in the course. So if you don't need more than the lecture notes and you're fine and you don't need to enroll, you don't need to email me. If you still would like to have the whole thing, the access to everything, then please do email me, and then I'll just add you manually to that course. And then there's already a link under Online Dynamics 2 you can click on, and it'll get you there. Okay. Quick review of what I did yesterday, and then I'll stop for questions. We were looking at details of the Bernoulli shift map, of the dynamics of the Bernoulli shift map, with the intent that we would establish this as the paradigm for a chaotic map. So whatever the Bernoulli shift map has, it would be a sort of a minimal set of properties under which we would call a map chaotic. And the list that we'll discuss various properties, and you will be asked to actually prove some of those. But the idea behind these properties is that we have a very explicit knowledge of the dynamics on the symbol space that we use to encode the Smale horseshoe map. We were able to establish things like topological transitivity, or you will establish some part of that in the homework, right? So this mixing property that two open sets always get mixed, and we looked at the conclusion, which again you will establish, but it's believable based on what we already have, is that the map has a dense orbit, meaning that there will be an initial condition such that if you hop in the symbol space, you will be able to get arbitrarily close to any point of that space. We talked about having an uncountable 7 non-periodic orbits, after all the periodic and asymptotically periodic orbits. And we talked about sensitive dependence on initial conditions, which means that no matter how hard you're trying to force yourselves to stay near an orbit, you will separate by a finite amount, and that finite amount is fixed for the whole space, okay? And I did spend some time on dwelling on that, because very often, erroneously, people associate chaos with sensitive dependence on initial conditions. I wanted to point out to you that that by itself is not a big deal. Any nonlinear system, or even any generic nonlinear system, or even a linear system would have it. This is a linear system, a saddle type linear system that has it. This is a nonlinear system, but it has another disadvantage relative to the saddle in terms of prospects, that it's actually confined. It only has closed orbits, so it doesn't have all the space that the linear example has. And yet, because due to shear on these closed orbits, this also has sensitive dependence on initial conditions. Anyway, so that by itself is by no means sufficient to define a chaotic map. What turns out to be a good set of sufficient conditions for a map to be chaotic is the one that I gave you here. There are other alternatives in the literature. So if you have a map on a compact metric space, so the space is you have a notion of distance. So this is a fairly generous definition. It can be even an abstract space. No wonder, because we want to establish this for an abstract mapping, which is the symbolic mapping, the Bernoulli shift on a symbol space, right? So it pays off to be general. So you have to have a metric on that, and the map just has to be continuous, and the space itself has to be compact with respect to that metric. So basically closed and bounded, right? And then M is topologically transitive, so it has this mixing property. That's the number one. Then it has to have sensitive dependence on initial conditions, and it has to have a dense set of periodic orbits. Which means that the regular core to the dynamics, even though it turns out to be unstable, remember that for the Bernoulli map, it's essential. And very easy to show counterexamples, although I just noticed before class that I messed up some of the notation. The little example that I had in mind was just the flow in a torus, quasi-periodic flow, never closes up. dense winding on the torus, yet nothing chaotic. Two linear oscillators with rationally independent frequencies have these invariant structures in their phase space. Each and every motion moves in a two-dimensional invariant torus. We discussed that last year, and we'll discuss that more in this semester. Just things running around quasi-periodically. Now that has the mixing property on each torus, but it doesn't have the sensitive dependence on initial conditions, because linear systems, because there's no separation on the torus, they run parallel. But you can just simply rescale that flow rescale, do a position dependent rescaling of time. Where I messed up here is that I had actually, as I noted, two different numbers here. I had an A here and I had a B there. It has to be the same number, same function, that is. If you insert, you have a set of ODEs, and you insert a common factor there, which is non-zero, right? Then just think about the fact that all that does, it doesn't change the vectors on the right-hand side. It doesn't change the vector field defining the differential equation. It just rescales the length of that vector, and it will do so in a spatially dependent fashion. So it will at some points speed up the evolution along the same trajectory and slow down the evolution along the same trajectory. So such a rescaling doesn't change the trajectories, but it does change the evolution along the trajectories, all right? And if you just, impose some periodic function there, and all of a sudden you introduce shear for the most part, so you will have sensitive dependence on initial conditions, you can achieve that, meaning that over time, trajectories will separate from each other because they don't travel with the same velocity. Their trajectories are still parallel to each other. They're running, on the torus like that, but, there will be a shift. So it's easy to introduce that. Yet, do you want to call the system chaotic? No way, because the trajectories are the trajectories of two uncoupled linear oscillators. You certainly don't want to call that chaotic, right? So what's missing, what stops you from calling it chaotic, although it has the mixing property and has sensitive dependence on initial conditions, it's the lack of periodic orbits, because all of them just move like that, right? Then you should say, okay, then what if I make the two periodic oscillators resonate with each other, right? So then I all of a sudden create infinitely many closed orbits on the torus. What about that? That's nice, but then you remove the mixing property, okay? Because the torus will be filled with periodic orbits. So each and every periodic orbit has a finite extent. Whichever way it's located on the torus, it's separated from the other one, right? It won't get arbitrarily close to it, okay? Because for the mixing property, you need that. So either way, you start fixing one property, then you mess up the other one. So this was just one simple example to show that these three properties are essential. Having said that, then sigma is then by definition a chaotic map, but sigma is topologically conjugate to the horseshoe map, which in turn is a model for the Poincare map of the Duffing oscillator, at least for a sufficiently high iterate of the Poincare map. So this way, in a very rigorous chain of conclusions, admittedly, I didn't do all the steps, but that's what the literature is for, to fill in some of the technical details, which get hairy. But we do have a reasonably complete argument that the forced Duffing equation and also the Rayleigh-Bernard convection cells after their instability are chaotic dynamical systems. So that's where we are now. We finally have a good handle on chaos in terms of definitions, but also in terms of what the orbit structure of chaos is inside. Now, I'll stop for a second if there are any questions related to this, what I've covered so far. Where I want to go next, I want to show that the toolkit that we've developed, symbolic dynamics, is not a one-trick pony. It's only effective in other. It's also effective in other contexts. These all the little things we've learned along the way. You don't have to start from a transverse homoclinic orbit of a time periodically forced system, even though that was my main motivating example. Any questions? Okay, if no questions, you can always ask questions later. Then I'll just pause for a second because I'm getting thirsty. Excuse me. Good. I want to then live up to the promise and show you how these ideas apply in other contexts. They're very different from mechanical systems or even fluid mechanics. So this would be an example for using symbolic dynamics ideas. And this will be going back, so this will be chaos in a model that I looked at. It was one of the very first dynamical systems that I looked at in this class in the first semester, the population dynamics example. So this will be chaos in a 1D model from population dynamics. So biology, essentially. And that goes by the name of the logistic map, not the logistic equation, which was the continuous version of this. It's a logistic map. If I said logistic equation, which was a one-dimensional differential equation, which we did look at, then you can laugh me out at this point, because there's no way a one-dimensional dynamical system can produce chaos, right? Which is autonomous. It's all it can do is move along a line. You know exactly, we had a full understanding of what it can do. It has fixed points and connections between fixed points, no chaotic behavior. For one thing, as we discussed, you need, for chaos, you need periodic orbits. For a one-dimensional system moving on a line, dynamical system, continuous time, there's no periodic orbit, because there's no way it can turn back on itself, right? Because that's the phase space. And you can't turn back on the phase space without intersecting itself. So one-dimensional continuous dynamical system has these constraints that prevent it from having chaos. We've also seen from Poincare the Bendixson theory that even two-dimensional systems on compact domains confined to compact domains, as long as they are continuous time dynamical systems, cannot have chaos, because their omega limit sets are one of whatever three types, right? Limit cycles or fixed points or connections among limit cycles. So that also precludes the chaos from existing. But what I'm saying now is that we're going to have a one-dimensional discrete map. And for discrete maps, amazingly, even one-dimensional ones can easily be chaotic. And they're very innocent looking. The one-dimensional logistic map is a mapping that takes the current value of a population and first imposes growth on that with some factor A. But normally it would grow by itself if there are, no predators. So this would be A, let's say larger than 1, okay? And that will lead to, in continuous time, it would lead to exponential growth. But we talked about this idea of real populations being resource limited. So they're also limited by predators often, unless you're on the top of the food chain. But even if you're on top of the food chain, you have the resource limitation. And the simplest model for that, as we discussed, is that you start penalizing the population for large numbers, okay? And you can have a factor here multiplying X to fine tune the model, but this would be the simplest form. So this is the resource limited population growth. Which is incidentally what everybody was trying to fit to the COVID virus at the beginning, the logistic model, when people thought it was a simple thing. And even scientists who have never worked in this area but knew about the logistic map started fitting like crazy last year and making predictions. But after when the second wave came and then the third wave and all that, then people have sort of given up, and they recognize that perhaps this is best left to virologists and epidemiologists after. It's not enough to know dynamical systems to just fit the logistic equation once to that way. But at the very beginning, as it was the virus population, there was no predator in the virus at that point. There was no vaccine, if you will. But basically you run out of clients, so that your resource becomes limited. So that was actually, in terms of, everybody was talking about flattening the curve, right? After the initial exponential growth. It turns out people were fitting these types of models to it, and it was very good. It was working very well for a while. So anyway, this is certainly a good model, and then it becomes a discrete dynamical system when you start iterating it. So the xn plus first will be then xn. I'm sorry, you have to apply this formula. AXN times 1 minus xn. So this is a very simple one-dimensional dynamical system. Okay. So and also, you know, what can go wrong in this one? You just keep going, and afterwards you flatten out, as you said, as I said, right, for the virus. But that fit was a continuous one-dimensional, continuous time dynamical system. Now we're talking about a map. Okay, so we're not constraining, you know, in terms of this, you know, continuous time dynamics of real life. We are not constraining that evolution to obey this role. Let me rephrase. When we postulate this in discrete time, we're not constraining the continuous time evolution to obey this at each and every point, right? We're just maybe sampling the population at equal times, and only at those sample points do we impose this role. In between, there's actually a lot of flexibility left, and that turns out to be enough for this to actually produce complicated dynamics, even though its continuous counterpart cannot do that, as we saw in the first part of the course, right? So this is not an ODE, but continuous dynamical system. So what does it look like? So we did see how to analyze these systems. I make an attempt to draw a fairly, you know, fairly square, because I need that. So this is close to a square. And this line, as usual, the 45-degree line is there for reference. And I'm going to pick the parameter value a equals 4. If I pick a equals 4, that's not necessarily because I'm fitting to any particular phenomenon, but it's a convenient choice because for a equals 4, this mapping maps the 0-1 interval to itself. So it's into itself. It doesn't get out. So it's a convenient choice of parameters, because it doesn't get me out from this interval. So the interval I'm showing here, 0, 1, 0, 1. Okay. And the graph of this, I'll try to do a reasonable job. So somewhere this is, you know, 1/2. It's supposed to be 1/2. And then in that case, it's just basically an inverted parabola. That's what it looks like. That actually touches. So it's always a quadratic function, right? And it's always a downward parabola. Just look at the formula. But then in that case, the maximum is at 1. So when I plug in 1/2 here, right, and I get 1/2, and that's multiplied by 1/2. So altogether, this is 1/4, but a is 4, so that gives me 1 at the maximum. Okay. So it's something like this, except that I want to make it bigger. And then the same on the other side. And this will be an imperfect drawing, clearly. It's supposed to be symmetric. Might be able to do better than that. Let me try again. Well, my 1/2 is really not entirely at 1/2. That's the main problem, but I think you get the idea. So it's a downward symmetric parabola. And pretty much the accuracy that you get from this figure will be enough. Modulo the hairiness that's unintended. Okay, so what do I see from this map right from the start without doing any analysis? Well, start from always the simple stuff, 2 fixed points. How do I see fixed points of one-dimensional maps when I plot them? Well, they intersect this 45-degree reference line, okay? So what I see here is 2 fixed points. One of them is at x equals 0, down here. And the other one is here. And just plug in to verify that this is at 3/4. Okay. What else can I do without too much thinking? Well, once I know the fixed points, I can worry about their stability. How do I get the stability of fixed points for one-dimensional maps? I need to linearize the map, which locally means that I take the derivative of the map and I look at the slope of that, right? Basically, if the slope in norm is larger than 1, that the map expands distances, it's unstable. near that fixed point, because we've got a fixed point here, nearby point there, map expands distances under one iteration. I'm moving away from the fixed point, right? Whereas if the norm of the derivative is less than 1, then the map shrinks locally distances. So then the fixed point is stable, even asymptotically stable. That's an easy calculation. So if I take f prime is for this choice of the parameter, which is 4. So it's like 4 minus 2 times 4 times x, right? At any point. So that's a f prime of x. Okay. So that's hopefully I get that right. So so that again, when I differentiate the first term, that's 4x, right? And then minus 2ax squared, the function. So that would be 4a. Sorry, exceeds my abilities. axn minus axn squared, right? So that would be 2a xn. That's what I've written here, right? 2a. Okay, good. So that would be 4 minus 8x, right? So if I plug in the first fixed point at 0, I just get 4, which is clearly larger than 1, right? So which means as that the 0 is unstable. If I plug in 3/4, then I have 6 here to subtract. So that's minus 2. So if I take the norm of that, that's also bigger than 1. So both of them are unstable. Okay, so is that so just by sort of a naive first check of what the iterates do? Let's see that. I'll pick a color here, and if I have a nearby point here, say I start iterating from here, then remember the Kopf diagram. I need to go up, right? And then, so this would be my initial point here that I'm showing. Then I need to look sideways to get to the 45-degree lines. So I would somewhere get there, okay? Then I would go up here further, because that means I'm refeeding that value into the map. Then I go here, right? Something like that. Okay, then I have to come down here. And I go horizontally again, and then I go up again, and there's no obvious pattern so far, right? Keep doing this. So indeed, I started fairly close. I mean, this is not a proof, but of instability. I already have the proof, but I just wanted to verify whether I miscalculated or not. Something indeed, if I start anything close, because the large slope there will just throw me out. And I'll do something like that. Same here, that large slope, if I start, say, here, which is very close, I have to look at sideways, and these large slopes tend to throw me out, and I'll go away. So indeed, both of them are unstable, which then makes this interesting because there's no obvious place where I would go asymptotically, right? The asymptotic behavior, even though I have fixed points, neither is willing to take me in any obvious way asymptotically. They seem to be pushing away the initial conditions I tried, so they're not good explanations for the asymptotic fate of this system. That's good. It's a good candidate for complicated dynamics. There's, however, another thing which is fairly simple dynamics, to some extent. Look at this. If I look at 1/2, which should be really in the middle here, and I iterate 1/2, and that means it takes me right to the top. Okay, like that. Okay, then my next iterate, I have to look sideways, and the only point I find on the reference line is here. And then the only point of the graph that I see over that, I look above and below, is actually this point down here. Okay, and then if I look now sideways, the only way I can hit the reference line is this. So I do, from that initial condition, from the 1/2, I do actually end up in the fixed point. So even though the fixed point is unstable, it does attract, it has the ability to attract other points, which can happen, say, with a homoclinic orbit, right? In the continuous dynamical system setting. It's unstable, but there are orbits that go to it. What a continuous system could not do, I could never reach that fixed point in a finite amount of time. Remember, that would be against a trajectory running into the fixed point that would violate uniqueness of solutions that I have for the ODE. There's no such constraints in the map. This is a perfectly well-defined map, and you can jump into the fixed point in a finite number of iterations. That's what I've just done. So even though the fixed point is unstable, you can get into it, right? So the one other observation, therefore, that one comes out of this, that one gets out of this, is that forward iterates of 1/2, okay, and of all its preimages under the map reach x equals 0 in finitely many steps. So how do I know that about the preimages of 1/2? Well, it's just the definition of the preimage. If something is the first preimage is 1/2, then it will be 1/2 after one iteration, and it will go through the same drill. Something is the second preimage of 1/2, then in 2 steps it will be 1/2, and then it will the same drill. So what are these preimages then? How do I go ahead and find the preimages? I maybe use blue for that. So how do I go ahead and find preimages? Well, the way to find preimages is that this is what 1/2 did, right? But I want to be in this position of 1/2. So I see, how do I get to 1/2? And the way to see that is that at this point, I start branching off here. I'm branching off there. And I pull them down to the reference line. I don't want to go all the way down, but I could. Okay, in fact here, well, I'm sorry. Here I have to go up, go to the reference line, right? So that means that this point here would be landing again in a finite number of steps here. But also if I'm here, okay, then this point after one iteration will do the same. So when I take preimages of 1/2 or preimages of any point, as a matter of fact, when I sort of pull that point down, I will always have in 2 directions to go. I've done that here. I went this way and then I hit this leg of the parabola, and I go this way and I hit that leg of the parabola, right? So at each taking the preimage of my point, any point at one step always gives me 2 preimages. So there's a binary branching always. And one of those, when I talk about 1/2, then clearly, let's do that branching. In the next step, I would get 1 here, and I will get 1 here, right? If I just go with the branch that does this, then amazingly, I find that the preimage of 1/2 also goes to 0. This branch, at least, right? As I keep stepping backwards. So there you go. One of those preimage chains takes me to x equals 0, but also in forward time, it's going to x equals 0. So I have a homoclinic orbit to x equals 0, right? And still, this is just sort of playing around, establishing the fixed points, taking into account symmetries of the map. What about the other branch? When I keep iterating the other branch, okay, I've done one backward iteration of that branch, right? And I ended up here. Again, this point will have the property that in forward time, it jumps into 1/2 and then is doomed because it has to go to x equals 0. But let's track this one branch, okay? And again, at each preimage, I will have 2 choices, because even now, I can either continue this way with the preimage, or I can jump on the other side and continue that way with the preimage, right? So what I've said remains true, that at each point, when I take the preimage, there will be a branching of preimage. There will be 2 preimages, and that is just related to the structure of the map. The map is not invertible, but not only is it not invertible, it's symmetric. So there's always two choices for stepping back, right? But if I keep following just one of these, then you'll also see what will happen. This. So in backward time, I will be spiraling into this other fixed point, okay, with this one branch. And I've constructed one such orbit, but I could have kept, following this track in backward time, and then jump here to the other component and do the same thing. So depending on how far I follow this branch of the pre-image before I start paying attention to the other opportunity, I get more and more of these orbits that in forward time, because they are starting from 1/2, they go to x equals 0. But in backward time, they go to x equals 3/4. And I have many of these depending on how far along I follow this track and go back. Following that logic, I can follow this branch for an arbitrary finite number of steps. But that finite number is not limited. So the conclusion is that I will have a countable infinity of orbits, right? That in backward time spiral into this point and in forward time spiral into the other point. So I have a countable infinity of heteroclinic orbits between these two fixed points. They go from x equals 3/4 to x equals 0. Okay, so that's kind of interesting. So again, I kind of show maybe I work this one out only. But at each and every point, remember, it's so easy for me to do this, but the actual pre-image taking would also involve this other branch, right? I'm just always following one branch of the pre-image when I go in backward time. Okay. Good. So that is, I would argue, it's already a surprising level of complexity from this little map that we have, countable infinity of heteroclinic orbits, homoclinic orbits, but still nothing that I would say it will determine the asymptotic dynamics, right? Because these are discrete orbits and nothing that is typical and nothing that is attracting. So I'm already finding things, but they're not, none of these are good candidates for asymptotic behavior, right? Everything here is pretty much unstable, right? So how could I then systematically describe this? First of all, this is the graph of F. So here comes the idea. I mean, motivated by this duality, that at each and every step, each and every pre-image will be either in this half of the interval or the other half of the interval, because I have these two branches, symmetric branches over them. The idea comes, and wait a second, maybe I could actually start tracking this orbit using an itinerary construct that we used in symbolic dynamics. What that would entail is that I take these two sets here, and I call from 0 to 1/2, and then with an overlap at that point from 1/2 to 1. So this is 1/2 and 1. I call this I1 and I call this I2. And of course, then I would have them here as well. For some of the things, it will be helpful to display them here as well. So this is I1 and that's I2. Okay. So the idea would be is describe the itinerary of the point. Each point with respect to I1 and I2. Now, the reason I'm showing this example, because this example also shows that life is not always perfect. In these examples, there'll be variants of the techniques that you will need to employ, because the example will have, some features that don't fit into the original one that we discussed. What are those features? First of all, this is not an invertible mapping. So my earlier construct, in which I was constructing itineraries, right, in which I recorded the present position, and then the first, with respect to some set subsets, and here those candidates are I1 and I2, right? So this would say S0, the first digit, would record where I am currently with respect to I1 or I2, and the next S1 will be where my first iterate will be, and so on. Okay, but what do I write here? Because each preimage has two components. So each preimage, if I ask where was I before, I have no definitive answer because I had a preimage here, I1 and also an I2. So there's no way I can encode this, right? I can write both numbers there and they will be equally correct. So this part is gone, certainly. The backward part, because the map is non-invertible. So backward encoding is not possible because F is not invertible. I mean, I know a lot about the preimages, okay, but I can't technically invert the map. Alex, please. Unmute.
Yeah,
okay.
Just a question regarding the 1/2. Does it belong to I1 or to I2? Or does
the 1/2?
Yeah.
So I'm going to address that now.
Okay.
It belongs to both, unfortunately. Right?
Okay.
That's the one limitation. It's good you spotted that. Right?
Okay.
So I've actually drawn it that way. That look that these two intervals actually overlap there, right there. Okay. So let me talk about that. So that's the first problem. So this is now the first issue, if you will. And the second issue is that 1/2 is the element of I1, and it's also the element of I2, as you have spotted. And now you ask, why do I do it that way? Why don't I just maybe contain 1/2 in one of them, and not in the other one, or I contain 1/2 in neither, right? The answer to that is that this whole construct that we use in symbolic dynamics, which heavily builds on Cantor's theorem, only works when you work with closed sets, because we will be having, if all goes well, infinite nested sequences of sets, and they are not closed. Cantor's theorem doesn't apply. So that's an inconvenience that's actually coming from the nature of this map being symmetric. We'll see other examples in which that doesn't arise, but I picked this example because it does arise here. And if you remove 1/2, you're punching a hole there, the machinery will not apply. And if you pick then smaller closed sets that do not meet at 1/2, then the problem with that choice would be that you escape from those sets. You can't contain the map. You just look at the map, right? So you have to contain the dynamics. It has to be an invariant partition that you do not leave. So with all these constraints, I have to go with this choice of 1/2, but that will also limit my construct. That means also that there's no unique encoding for preimages of 1/2. Now the preimages of 1/2, they double themselves in each and every step, right? So when you then imagine an infinite binary tree, which keeps growing as you ask, what order of preimage this was, you have more and more. So ultimately, this affects a countable infinity of points. They all will at some point hit 1/2, and the minute they hit 1/2, they cease to have a unique symbolic encoding because they both belong to I1 and I2, right? So that actually won't work. What's the idea? Well, I picked this example because there's an alternative. Instead of trying to pick a trajectory and then encode it uniquely, you could go the other way around and say, let's pick an encoding in the anticipated symbol space here and try to show that for that encoding, there is a unique trajectory. Okay, so in this direction. It doesn't go the other way. So one cannot show that the trajectory has a unique encoding, okay? But if once I fix an encoding, okay, that should actually hopefully give a unique trajectory, okay? And we'll see how far that gets us in this case. So the modification of the construct that we used for the horseshoe. So seek a trajectory for any symbol sequence. So in other words, try to go the other way around. So define a map psi, which will be a mapping from the set of not bi, but single, actually infinitely long sequences. So these will be of this type, okay, into 0, 1, all right? And I'm trying to find points. Again, I give you, somebody gives me an encoding, and I try to find a point whose itinerary is precisely that, rather than going the other way around, okay? So then in that case, if I take S, what defines this psi, or is it phi? Did I use psi? I forgot. Oh, this is psi. Oh, it's okay. Would be the following, that it would be of course, when I take S, that means I'm feeding in a particular symbol, right? Sequence. So the way I seek the corresponding point in 0, 1 is I try to interpret this symbol sequence as it was the encoding of that point. So that means that the X point into which I'm mapping this should be such that it should be the element of IS0, because that's what this symbol is hopefully telling me, that I'm currently in IS0. But I should intersect that with the first preimage of IS1, because this is what hopefully this symbol sequence is encoding, that after one iteration I will be in IS1. And then I have to intersect that with the second preimage of IS2, and so on. So that would be then the image of that point, of that symbol, S. Now, this, of course, brings in the question that, is this well-defined? I can prescribe anything I want, but this is an infinite intersection of sets, which may not contain a single point, or may not a single point, or it may contain multiple points, and that means it's not well-defined. So the question is this well-defined? Does it give me a unique point? And I'm not going to do everything here in detail, but I'll do most of it. So the key observation, which is a useful thing that will also come up in other examples that you do in this area, is the following: that if J in this interval, the unit interval, so J will be just any, let me indicate that here. I'll need to pick another color, something I haven't used before. I pretty much have used that for the, all right, this funny one. So maybe, so if I take a J, which is just a closed connected interval somewhere, and I look at its preimage, that's what I'm going to be doing down there, but I just show that here. How do I look at the preimage? Well, I go horizontally and I map it down here. This is one component of the preimage here, okay? But I go for the other component as well. It's somewhere down here. It's supposed to be symmetric, but won't be. So what you see here is these are the two, these two together form the preimage of J. Okay, and this was J. And J, as I'm writing here, I'm defining what it is a closed, connected set. Okay, so it's a closed interval in this case. Then what you can read off from here, that the intersection of the preimage of J with either of these IIs, these are the two intervals, which is this and that, is also a closed and connected set. okay? Then I, little I, intersect preimage of J is closed and connected. In fact, non-empty. If J was not empty to begin with. Okay. So this observation actually turns out to be enough. For most of the work to show that this is well defined. So why is that the case? So if I then define, I try to go about this set here, this one that I'm constructing. So first I dissect it and look at this part of that set and see what that gives me. So if I define that part of the set, and I just call it I S0 S1, which will be I S0 intersect preimage of I S1. And perhaps you see immediately why I've gone through this. IS1 just qualifies for a J because it's it's one of those, the I1s or the I2s, one of these large sets, right? This one or that one. It certainly qualifies for that. Then this is non-empty, closed, and connected. Then if I start growing this set, which means that I'm really starting to execute these intersections, but by one more step. So I then have IS0 intersect first preimage IS1, second preimage IS2. This doesn't look like anything I've written here, so it's not obvious how immediately I can use that observation. But with a little work, I can bring it to that form because this is IS0 intersect F inverse, not inverse preimage, right? IS1, and then I write intersect F inverse IS2. So what I did here, I've just opened up another parenthesis, okay? And then I say, all right, but then again, this looks like what I've been postulating, not postulating, reading off. This is sort of an easy statement to make. This qualifies for J. So therefore, the output of that is that operation. This is non-empty, closed, connected. And then I take that non-empty and closed connected set. So this is now my new J. And again, apply the same observation in this context. So what I get out of this, so this whole thing is not empty, closed, and connected. So then I guess you see the pattern that I will be able to do this in each and every step in this construct as I grow my indices, but in fact, as a matter of fact, shrink the set of points for which that itinerary is valid, say up to S, what index did I use here? N. So I'm trying to work out what this set is to which X belongs, the image of that encoding. So this will be a more and more specific set. A smaller and smaller set of points will satisfy it, right? And my hope that ultimately shrinks down to a single point. And I'm heading towards that. And the observation is that I can just keep opening parentheses here, rewrite this. Right? So I also then keep up opening when I write this infinite intersection here. I keep up opening up new parentheses and always then have yet another preimage there. Blah, blah, blah. And ultimately, the last one will be let me write out the last one. It will look like this. I, S, N-2 intersect preimage of I S n minus 1 inverse F ISN. That's the last one. And there were a lot of parentheses there to close. But then I start from the end. This has the same structure as this observation here. So sum ISN minus 1 in this case, which was, when I was looking at the encoding of this symbol, the last digit was SN. So ISN minus 1 intersect the preimages of ISN. That's what comes out to be, but that's going to be my J, closed connected. Okay, then the output of this is closed connected. That's the statement. Sorry, this is closed and connected. So therefore, when I apply when I look for the preimage of that and intersect it with ISN minus 2, that's again closed and connected and non-empty. And I go recursively, finally get the same thing for this whole string. So what I end up getting is I started with IS naught, and then the one that was one longer than that, which I did first here. Okay, it's closed, connected, non-empty, and it's contained in the previous one because when I go recursively, I always intersect what I already have with further information, right? So I always start with this chain, always contains the prior ones that I have already computed. So this is a non-empty, closed, connected nested sequence. So by Cantor's theorem, it's not empty. So this intersection, this infinite intersection, is not empty. But I also know a little bit more, because you don't need connected for Cantor's set. You just need closed and nested. And here we also had connected. So each and every component is connected. So you're not developing new and new points or new and new sections as you would do when you do the Cantor's construct. So you're actually shrinking towards just one component, right? So it's also connected. There's a little bit of extra work here to do, which I'm not doing, that at each and every point, you're actually shrinking. So shrinking with a uniform factor that doesn't go to 0. So you can give a uniform estimate by which you're shrinking. And if you're shrinking by a uniform estimate, that you cannot limit on an interval, a connected interval of finite size. So you have to keep shrinking towards 0. And that will imply that this intersection that we're looking at, in fact, consists of a single point. Right? So it can also show is that the length of IS0 blah, 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 S1, Sn goes to 0, as n goes to 0. So the intersection is a point. A single point. And that comes from the connectedness. Because just because you're going towards a set whose length is going to 0, it doesn't mean that it would have to be a single point. That's why I'm using it as a connected set. So that means, however, that psi is well defined. It does give me a single point. So psi is well defined, can also show this will not be a whole lot of work, or would not be a lot of work, that it's continuous in the metric that we have. we have already used. Which means that if you take two symbols that are close to each other in that metric, remember the metric pronounces two symbols close if they agree on large central blocks, then the encoded points that come out from this construct will also be close to each other. The closer you make the preimage points to each other in the symbol space, the closer the others will get to each other in the real space. That's believable, I think. So I'm not going to do it, but you actually have the machinery to do that here. Simply because then, you know, these, all right, so I skipped that. I think that part is believable. The, what else do I need to do? The last observation is that to make that by definition, one iteration of f is equivalent topologically to one iteration of sigma. In other words, even though I'm coming from the other direction now, I'm coming from the symbol space, I can still establish that doing one Bernoulli shift in the symbol space is on two symbols. So one of them is one that I picked, and the other one is the iterate under sigma, is the same as taking the point x, whose symbol encoding I started, symbolic encoding I started with, and doing one iteration on f on that. In other words, when I do that, then the iterated symbol sequence will precisely be the encoding of that trajectory, right? So why is that by definition? It's just reading off from the encoding, right? That if I have S0, S1, and S2 as a symbol sequence, okay? So that means that by construction, because that's how I did the nested sequences, it means that X is in IS0, right? And what did I do next when I was building that construct? I was constructing this nested set, which was shrinking down really just to one point finally, by requiring that point to be in IS0, but I also wanted that point to be in the first preimage of IS1, which means that when I map that point forward in time, then I will be in IS1, because for me to be in the first preimage of IS1 by definition means that if I mapped forward, I will be in IS1. Likewise, if that point was also engineered to be in the second preimage of IS2, it means that if I then take that point and apply f twice to it, then the point will be in IS2. So that's the way then to read this encoding, that fx will be in IS1, and also f second iterate will be in IS2. That's how I constructed that set. But with that knowledge, I see that the encoding associated with f of x, just read it off from here, right? And so on. So it's S1, S2, and so on. Okay. But then S1, S2, and so on is just the Bernoulli shift map applied to S0, S1, S2, and so on. Okay. So that's really just by construction. It's always when you build an itinerary type encoding, then the Bernoulli shift map will always, if you manage to do that, it's not on a given that you're able to do that for any dynamical system, but you're able to establish that one-to-one correspondence, then the corresponding dynamics in the symbol space will always be just running your itinerary, right? Once you create an itinerary, just following orbits, then in the symbol space, you will be just, you know, on deciphering that itinerary. So it's always the sigma map. So what do I have here? It means that I started from the symbol space now, and on that symbol space, I had sigma. But I came down from that symbol space as opposed to going up with the construct because I had these issues with the encoding, you know, with the 1/2 being part of both intervals and also the preimage being problematic because the map is not invertible. So I came down to that sort of physical space in which the logistic map lives and in which my mapping lives. And in this case, I cannot invert psi. So remember, psi is C0, well-defined, but not invertible. Nevertheless, the way I've drawn this diagram does commute. So that means that if I can go this way, I can, essentially I've been modeling sigma itself. So I would say that doing this route is going the same as going to be the same as going this route. So that means that if I apply sigma, what is this, psi first, and apply f second, which is I'm going this route, it's just the same as applying sigma first and applying then psi next. So I apply sigma and apply psi. And much as I would love to express this for f, as we would have for a topological conjugacy, I cannot do that because that would involve taking the inverse of psi, which doesn't exist. So I leave it like this. And this is a slightly weaker notion of conjugacy. It's actually called a semi-conjugacy. Reason is that you have this close relationship between the two maps. We have seen, right, the symbol sequences, when I move in F, the symbol sequences will move by sigma and so on. And so this is like a very close relationship, but what stops me from inverting that psi is that problematic set, all the preimages of 1/2. That's the culprit. That's the only reason why I cannot invert this. So I understand very well where psi goes wrong in terms of inverse. So this, however, means that, but they're still pretty intimately connected for all other points. So F and sigma are what we call topologically semi-conjugate. And that turns out to be enough for this map to be chaotic. I'll just pronounce. So this is enough for F to be chaotic, even though strictly it doesn't satisfy the original definition. Why am I willing to give up and compromise on that definition? I tell you why. Because on the set on which the invertibility fails, the set on which the one-to-one correspondence between the two orbit structures and the dynamics fails is a very well-known set. That's just the preimages of 1/2, those points, and all the preimages of 1/2 either converge to 0, so they're asymptotically a fixed point, or converge to 3/4. So I have a countable set, countable infinity of points whose ultimate behavior in forward time, I know, they all go to 0. And in backward time, they either have been coming from 0 or they have been coming from 3/4. So all these guys are either homoclinic orbits to this trivial fixed point or heteroclinic orbits within the two fixed points. None of those are chaotic orbits, right? So what the set on which I'm compromising is small because it's only countable, and it's not that interesting. So even when I take that set out, I still have the same incredibly rich orbit structure of sigma, the countably many periodic orbits, the dense orbit, the non-periodic orbits, and everything, all the goodies that I have there, right? I'm just throwing out a set of points which are kind of interesting, but they were not the ones that were making me all that excited or made the map chaotic, right? So I can even sort of go further, is that once removing the preimages of 1/2 would actually give me, say, I tilde, which would be I tilde equals I minus, let me not write this in notation, all the preimages. that's still a very large set. And on that set, I can actually invert because those are all good unique encodings. And on that set, I can write F equals, it's F tilde, but the wrong way. Which way I want to do this? F tilde equals psi circle, and then I have psi inverse. Okay, so that's good. So it's only the set of points on which has chaotic orbits. All right, any questions on this? This already shows that, I think, two interesting things. One of them is in a very simple example, no a priori small epsilon homoclinic orbits forcing nothing. I would have thought, first, being faced with this example as a completely boring example. I mean, how complicated can logistic growth get? Well, it turns out if it's a discrete dynamical system, it can get very complicated, just as complicated as infinite dimensional coin tossing or random jumping between two components, one or two, in terms of your observations, right? Because that's what chaos reflects itself in here, that there are two states, the I1 and I2, and you can have these super complicated patterns involving both. Maybe you're in one of them for a long time, and then you jump to the other one, come back. So pretty much what we had for the Duffing equation. But the existence of the homoclinic orbit here, which actually did exist, played no role, and the heteroclinic orbits either. Now, so that's one lesson. And the other lesson is that life is not always perfect. So you may have to make compromises in terms of the machinery, and you may get slightly less than the full chaotic map, but you're still getting all the goodies of a chaotic map, okay? So one has to be prepared to generalize the construct that you've already seen. So I just want to very briefly talk about usual generalizations, because they also then give you different types of chaotic dynamics, because even within chaotic dynamics, you can have different levels of complexity. This is, in fact, the Bernoulli shift map turns out to be the simplest you'll ever have. So the next step would be then generalization of chaotic dynamics. So in what ways can you generalize? I think, again, sigma was the prototype. You could ask, why sigma? Can I make it more? How would I make sigma more complicated? Little sigma, that is the Bernoulli shift map. Well, I can make the space a whole lot larger. I would like to preserve the shifting mechanism, because if I give that up, then I'm giving up the easy ability to reconstruct orbits. So I like the fact that I'm just shifting around, right? That enables me to discover the space. But I can make the space certainly more complicated. How can I make the space more complicated? It's already doubly infinitely long. I can allow for more symbols, right? So I can make the symbol space more complicated. So sigma capital N would be a version of the symbol space in which I build S as, again, doubly infinitely long. But the SIs are now taken, say, from a set of integers ranging, say, I start from 0 up to some n-1. So I have a total number of n symbols, not just 1 or 2, but maybe up to 10 or up to 17 or up to 100. So all of a sudden I have a larger variety of things. And indeed, in a real life problem, there are many different states potentially with respect to which I'd like to encode the dynamics. It's not just two states. In the problems we have seen so far, there have been two dynamically distinguished states. You can have many, all right? So that's one way of generalizing. But another way of generalizing is actually acknowledging that even though you have many states in a system, in a typical physical system, you do not necessarily have the ability to jump from any of those components to any other component in one step. maybe you have to actually work your way around, or you may never be able to get from one of those distinguished states to a particular distinguished state. You may be able to get to others, right? So in a real-life system, there will be restrictions. So there will be constraints on admissible symbol sequences. So these tend to arise. So somehow I have to have a way of enforcing those constraints. What does that mean? It will mean in practice that not all these symbol sequences will be allowed, but I might have a rule that, hey, if this one is 1, then I'm able to go to 8, 9, and 11, but I'm not able to go to the rest. So I will have to have kind of a mask that I have to run in a symbol sequence, all possible symbol sequences, a filter, and sort out the ones that are simply not allowed because the real-life system that I am encoding doesn't allow for that particular transition. Not doing this would artificially enlarge the symbol space, and it would give me itineraries that do not exist, in fact. Right? So how do I enforce such rules? And there's a way to encode them. So fix these in a tool which actually, if you've ever seen or will see, or you haven't, doesn't matter, but if you've seen the theory of Markov chains, that has something very similar. It describes possible transitions in probabilistic terms. This is still deterministic, but in Markov terms, in probabilistic terms, will tell you what's the probability of you getting from here to that state or from that state, and that gives you a matrix. Okay. Now this is a deterministic state. We're not going to have probabilities. We're not going to have in betweens. I'm either able to get from here to there or no. Right. So 0 or 1. That's how we're going to enclose it. So this is a transition matrix that we will associate with a lot of the real life problems in which you have chaotic dynamics. And the transition matrix will be an n by n matrix. And the elements of it will be taken from 0 or 1 because they will give you a yes or no answer. And with that, I can augment the definition of the space with that transition matrix. So I'm now using n symbols, capital N, but part of the definition of the space is now this transition matrix. And what it does to the space is that a priori, of course, I could have all the elements from the space, but I'm going to restrict these now to those for which I find that the capital A, Si plus 1 is non-zero. So I a priori consider all symbol sequences, but then I start looking at adjacent patterns in them, and I will check in each and every case whether that pattern, which, this is one symbol and this is the other symbol taken from this set, is something that's encoded as a go in the transition matrix, right? So I go take those symbols, this is, 1 or 3, and I go to the 1, 3 element of the transition matrix, and I check whether that's okay. If it's 1, it means okay, so that means that transition is allowed. If it's not 1, but it's 0, then I will not include it in the space. Right? So this will be basically not the full space of symbols that you could make out of those n symbols, but there will be all these restrictions, and they're all encoded in this matrix A. What would be the simplest example? Suppose that I look for a set of 2 symbols still, so not to jump too much away, but now I'm adding a transition matrix, and always start with something simple when you don't yet have experience in something. So what's the simplest matrix? Well, I'm not going to do full zeros because that means no transitions from any state to the other, but let's just say identity, right? So that means that the admissible transitions encoded will be that you have a bunch of symbols by infinitely long sequences, and then a 1 and 1 is certainly allowed. Okay, so that's a check according to this matrix, because A11 is 1. And this can happen anywhere in the chain. The A22 is a set of 2 symbols, right? Here. So the sigma 2 would be the set of symbols for which Si is 1 or 2. And that's the space we've seen before. We've denoted it simply by sigma without the 2, but in this context, now I need the 2. This is still okay. However, there's no way I can ever see something like that or something like that. Okay, so these are not okay, because the corresponding A12 and A21 are 0. So when I assemble my space, that's a no-go, any such combination. So what does that mean? It means that ultimately this space, sigma 2a, if you think about it, nothing else but the infinitely repeating fixed point 1, 1 for the Bernoulli shift map, and 2, 2, because these are the only 2 fixed points, symbols that are allowed, which is bad, because that means I've really overdone it. I took a space which was a nice Cantor set, I assigned some rules to it, which seemed like benign rules at the beginning. I completely killed off the possibility for any chaotic dynamics, because just by imposing this transition matrix, I took the infinitely many elements, uncountable infinity of elements of this Cantor set, and narrowed it down to 2, not even countable infinity, just 2. So the matrix, the transition matrix, has an incredibly important role in defining the complexity of the space. And you can easily overdo this and lose any possibility for chaotic dynamics. So this is basically 2 fixed points in the phase space, for 2 fixed points for the Bernoulli shift map, nothing else. So that means no chaotic behavior. On this space. So it would be nice to have an a priori check whether when I try to encode something and I will encounter these transitions that I have no choice but have to encode. Otherwise, I'm going to get symbol sequences that never exist in real life. I have to have a check by which I can go ahead and see whether this is leading to chaotic dynamics potentially or not. Okay. Now, first some definition before I go to the check. Then sigma on this space, the Bernoulli shift map on this space, some terminology that you would find in the literature is called a Bernoulli, not shift, because I'm limiting the reach of sigma. It will not be able to act on all symbol sequences. So for that reason, it's called the Bernoulli subshift. And there will be another adjective that people append to it in this context, and it will be called of finite type, because I could actually go ahead and do an even more drastic generalization and allow the number of symbols to be infinitely large. And that's a whole other level of complexity I'm not going to go into, but maybe for partial differential equations, when you establish chaos there or other infinite dimensional dynamical systems, you would need that, but we're still doing finite dimensional dynamical systems with finite symbols. And so the finite type, which means that n is finite. So the term that you might find is in the literature is a Bernoulli subshift of finite type. Okay. And the minute it's a subshift, I have to say why it is a subshift. What am I limiting? So then with the transition matrix A. Okay. Now comes the statement that I wanted to. It's a very important. See the references that I've listed, and there's no way. I mean, this is more complex. I can't show that here, but it's a very simple statement, a very easily verifiable statement about the space and about sigma. So assume that A, this transition matrix that really defines the space and ultimately therefore the nature of the shift map on the space, assume that A, the transition matrix, is irreducible. That's a new term here. So i.e., there exists an integer k, and I think that I allow that to be it has to be a positive integer because it will refer to iterations of A, multiplications, such that when I look at the kth product of A, this matrix by itself, so essentially you're iterating the matrix as you would with the transition matrix of a Markov chain when you try to iterate a Markov chain. So imagine that I'm just iterating this, multiplying this a constraint matrix by itself, and I find that there exists a number of iterates for this matrix, which is k, it's an integer, such that when I check the elements of the matrix, then none of them are 0. So what does that mean? It means that A has become, under k iterations, A has become a full matrix. So maybe initially it wasn't. If it was a full matrix to begin with, what was it full with? It was full of ones, which meant that there was no restriction whatsoever. But in a general case, when you would apply this construct to begin with, some of those elements will be 0, meaning that certain transitions and hence certain symbol combinations are a priori excluded. However, we call A irreducible if that somehow goes away under iterations of A, that I find an iteration number, a multiplication of A by itself to the kth power, on which this is no longer the case. So all the entries of this iterated matrix will be non-zero. I can't say that they're 1 anymore because I'm multiplying the ones and adding them up, right? But the question is whether they're zeros or non-zeros. And if I find that all of them are non-zeros, then I will call K irreducible. Then under this assumption, good things will be happening. Namely, sigma NA, despite all the modifications and all possible, despite all the possible unintended oversimplifications of the space, if this is the case, then sigma NA is a Cantor set with all the defining properties of a Cantor set. So it's totally disconnected, perfect, closed, non-empty. Okay, so it is a complex set. In fact, potentially a whole lot more complex than the original sigma that we have seen, because we now have a general N here. And the good news is that also then sigma, this Bernoulli subshift of finite type, is a chaotic map. So it basically comes down to linear algebra, right? Essentially, but not even necessarily knowledge of linear algebra, just having a code, if you can't do this by hand, that multiplies this A by itself a few times and see whether you have reached a point in which it's full. In that case, you have not oversimplified, you're not looking at anything sort of a trivial symbol space, and the shift map on that space will be chaotic. So if you have been investing in encoding your dynamics and you got this symbol space and this map on it, then you're done proving that your dynamics is chaotic. So to understand a little bit this irreducibility, that's the last thing I want to say. So why today? Why is it such a magic property that all of a sudden that should assure us that we are working in a complicated space, in a complicated map? And I did an example, I think, in the notes. So let me do the same example. So assume that K is not too high, but also it's not outrageously low either. It's not 1. So assume just that the third iterative of ij is non-zero. So all those elements are non-zero in the third multiplication of A by itself. Why would that have any implications for the structure of the space? Or what is the implication? So when you then really write out what that is, how do you get the third product of a matrix? Well, this is basically a tensor product that I'm just going to write out in pedestrian notation. If you remember your linear algebra, how you get matrix products from elements of the matrices. So the first, it will be A 3 times big A with the appropriate indices, right? And the first index has to be I, because that is I, and the last index has to be J here. And in between, I'll be summing over the remaining variables. I will have to take all combinations. So maybe this is IK, and this is KL, and this is LJ, and I'm gonna be doing the summation over KL. Do I have enough? KLL, yeah, there's two of them. And I and J are fixed. That's correct, okay? So if this is non-zero for all ij, so for a given ij, that means that when I took all the possible combinations of the original A, which is not on any power, and I was trying to build these chains that you see here, these products, right? Then in this big sum, at least one of these terms was non-zero. We're building this out of only ones and zeros. The A has either zeros or ones. If this whole product here is non-zero, that means that at least one element of this product had to be non-zero. But the only way it could have been non-zero is that one of these chains that I have built here had 1, 1, 1 here, right? Okay, so that means that there exists K, L, such that AIK is equal to, not only is it non-zero, I know exactly what it is when it's non-zero, it's 1. So AIK is equal to 1, AKL is equal to 1, and ALJ is equal to 1. So what does that mean? It means that even though I was not able to get necessarily from I to J in one step, but a transition from I to K was certainly okay in one step. Then a transition from K to L is allowed in one step, and the transition from L to J is allowed in one step. So even though I can't go from I to J necessarily in one step, but in 3 steps I can. So none of the states are unavailable to me a priori. If I wait long enough, I'll be able to go from anywhere to anywhere, right? So that is then behind the statement that, okay, then all of a sudden my dynamics is not limited. It's just that I have to wait a little bit more, but ultimately I'll be able to discover the whole symbol space, okay? Or according to the whole initial space. So that means that a 3-step transition from any I to any J is possible. So then you might ask, what went wrong with my original example, in which I looked at the space C2A and my A was this really nice simple matrix. And I found that things were not going well for that one. It wasn't producing chaotic dynamics for me. Now, AK, any power of AK, is the identity. So it's just the identity itself. And the identity will never become a full matrix. I think it should be there exists KLM, not for all. You're right. Thank you. For all IJ, but for all KL. So there exists KL. Thank you. All right. So where I was at is that no matter what power I raise A2, it's always going to be the identity matrix, okay? And it's never full, never a full matrix. So that means that A is not irreducible. So that's all right. I ended on a negative note and never end on a negative note, but I have to stop for today. What I'll do next time is I show you a very interesting, really real life example in the sense that this does occur in numerical processes that you would run an iteration on a computer. and you can get into chaotic dynamics, even though we would normally hope that the iteration converges, especially when we're talking about an iteration which is such a broadly used iteration as the Newton-Raphson iteration, which is the king of iterations. It always works except when it doesn't. And it turns out when it doesn't, then things can go really bad. And when you try to describe why things go bad and look into that, and people looked into that, I think maybe in the 80s, I don't have the reference yet, they looked into that, they were able to show some beautiful chaotic behavior there. And to show that, you need the full power of everything we've done so far. So it's not going to be a simple type of chaos in two symbols, but several symbols, and also it will be a non-trivial transition matrix. But it's a really interesting result. I'm not going to draw all the figures next time in detail, but I'm going to skim through the notes and explain everything in detail. So, and that's pretty much where I will end discussing chaos in the first half of the next lecture, and then we move on towards the rest. So I'll stop here and take any questions if you have. Once again, I'm waiting. I'll send an email, but if you need or like to have access to the remaining materials in all the dynamics and chaos one, just send me an email. And if you don't have access because you didn't take it last semester, then I'll add you to the list. Okay, thanks. Anybody? The last chance before the weekend. Okay, if not, then thanks for your attention and have a good weekend. See you next week.